Alright, let's get started. So today we have a guest lecture by me on relative dynamics in the restricted three-body problem. Just a little introduction about myself for those of you who don't know me. My name is Manuel. I'm a fifth-year PhD student in the Space Rendezvous Lab under Professor D'Amico. I got my bachelor's from Purdue in 2020, so boiler up, and I came here right after that, started my master's, and then continued on to the PhD, where I've been studying circular restricted three-body problem, absolute and relative motion, and trying to characterize those dynamics better. And one other quick note is I've also worked on space technology policy with Professor D'Amico and some of those SLAB postdocs for the Stanford Emerging Technology Review. So today we're going to cover the motivation of why we're talking about this subject, and then do an overview of absolute motion in the CR3BP, just to level set and make sure everybody understands where we're starting from. Then we'll compare the three-body problem and the two-body problem, and then we'll spend the big chunk of the class talking about the actual relative dynamics models, going over a survey of some of the models out there, and then do a deep dive into CR3BP relative motion in local frames and local toroidal coordinates as a way to parameterize that motion in local frames. And so the whole thing hopefully will wrap up in about an hour and leave plenty of time for Q&A. So to start out with motivation, like why are we doing this talk? Like, is it just because Professor D'Amico and Paul told me to? Or like, what's the importance of this CR3BP and, well, just three-body motion in general that requires a whole different lecture from the relative dynamics in around Earth orbit that you've been studying so far? Well, there's many applications with multi-body dynamics that aren't captured by two-body motion. For example, deep space exploration. These are some images from the Europa Clipper mission. So that involves visiting Jupiter's moons, and so it's influenced by both the forces of the spacecraft would be influenced by both the forces of Jupiter and the moon, and the dynamics would become different. And so those missions require different dynamics models. The James Webb Telescope, who most of you probably know of, it's actually perched at in a halo orbit around a Sun-Earth libration point, which we'll define the libration points later, but it's in a very special orbit that wouldn't be possible without leveraging three-body dynamics. And that allows it to have the ability to capture those great images and make those scientific discoveries. And then the biggest motivator is, or called the moon rush here, where we went to the moon 60 years ago, but now everyone's trying to get back to the moon. And it's not just the United States this time, it's lots of other countries, China, India, Japan, as well as private companies too, like Intuitive Machines, which attempted to land a rover. So we see all these different companies are launching satellites to the moon, around the moon, launching rovers and landers, and then NASA, of course, with the Artemis missions, is planning to land the first people on the moon since the Apollo program in 2028. First, they have the crewed flyby in 2026, and then 2027 to 2028 will land the humans on the moon, and then potentially even have the Lunar Gateway starting to be assembled in 2028, which is a collaborative approach with contributors from the European Space Agency, Canadian Space Agency, JAXA, etc. And that would be a big step forward, having a lunar space station in orbit. And so, but there's many things needed to accomplish those goals, right? And this is a big priority, both from a civil, commercial, and defense standpoint, where they all want to grow their cislunar presence, and they want to accomplish many new mission needs, including rendezvous proximity operations and docking or RPOD. And that'll require distributed space systems for some of those. But the biggest hindrance right now is, you see that pull quote on the on your right over there. So it says 2-line elements are not sufficient in the 3-body problem. Like the state representations we have there right now that we use for the 2-body problem and that enable us to track objects and maneuver objects and perform RPOD with distributed space systems in Earth orbit are not sufficient. So we need to come up with new dynamics models, both for absolute and relative motion, in order to characterize what's happening in cislunar space. And these cislunar orbits, which we'll get into very soon, can be irregular, unstable, and chaotic. But that's both a blessing and a curse, because it's hard to characterize, but if we can leverage it properly, then we can achieve things that we wouldn't be able to in Earth orbit. So let's dive into the 3-body problem. Like I said, we're going to start off with just some background on the circular restricted 3-body problem before we get into the relative motion. So what is the 3-body problem? Well, we start off with 3 bodies. And then we're going to assume that those bodies are point masses, spherical point masses. And then we're going to, let's just think of planets, stars, moons. And then we're going to add a restriction. The restriction is that the mass of one of those, could be like a spacecraft, is much smaller than the other 2. And then we add the circular part of it. And so we're going to assume that the 2 large masses orbit in a circle around their common barycenter, which is the thing with the X in the center. So as it orbits in that circle, this allows, if we define a coordinate, a reference frame that's aligned with that circular rotation, called a synodic frame, that allows us to more easily evaluate the dynamics and the motion and visualize the motion that's going on in the CR3BP. Now, forgetting the jokes and stuff, we think of like a real system like we were talking about. It's the Earth and the Moon. Here, the Earth is the bigger body, and then the Moon is the second primary, like orbiting around in this circular motion here. And then we have our third body, the small negligible mass spacecraft as well. And then the other neat thing in the CR3BP is that these equilibrium points, especially when we use this synodic frame, this rotating reference frame, there are points where the gravitational forces and the centrifugal forces cancel out. And those are called libration points. And so, well, you might have heard them called as Lagrange points before. I like to use the term libration points, which is more inclusive, because Euler actually discovered the collinear points L3, L1, and L2 first in 1750, before Lagrange discovered the L4 and L5 10 years later in 1760. So I think it's better to say libration points in general. And so periodic orbits can form in the rotating frame, such as you probably heard of halo orbits or NRHOs. Those can form around, in the vicinity of these libration points, these equilibria, specifically around the L1 and L2 points. Those are the ones that are most useful for cislunar mission planning. And that's where a lot of the focus is on in the research currently. So getting into the actual math of it, as we defined, there's 2 point masses moving in circular orbits around their barycenter, and the mass of the spacecraft is negligible. Here's our equations of motion here, which are traditionally non-dimensionalized and represented in the synodic rotating frame. There's the key thing here, though, that's very important. There's no closed form solution. The only way to find a solution to say, like, where are we going to, be at point, X minutes from now, is numerical integration. That's very different from the two-body problem where we have Keplerian motion, you have the closed form solution, the Keplerian orbit equation. So these equations are just fundamentally difficult to work with. One thing to note, though, is that the total effective orbital energy is conserved. Sometimes it's expressed this way as the Jacobi constant, where we have this pseudo-potential term minus the total kinetic energy. Yeah.
This is just to check if some of you can recognize the structure of those equations.
Well, you're spoiling it. I'm getting to that.
I thought you were going to the next step.
Oh, yeah.
Okay. Sorry.
So diving a bit deeper to so what those partial differential terms are, we have, so this is a pseudopotential. What I mean, why is it not a potential? It's because, so we have, you recognize like these terms here, this is like your standard gravitational differential equation, like not differential, gravitational force here. We have mass over distance, but then we add this this term here to account for the centrifugal force. So that's why in the synodic frame we have this pseudopotential. And then that gets thrown in here, the partial derivatives with respect to each coordinate get thrown in and produce these kind of convoluted terms, which is where most of the difficulty comes in integrating the CR3BP equations of motion is from the pseudopotential. But just so you understand like what we're working with here, which will become more relevant later when we get into linearizing these equations of motion in various forms. So, as Professor D'Amico spoiled, you can see that there's actually a comparison to be made between the state space systems in the CR3BP that we just saw and the two-body motion, relative motion. So we have the Hill-Cauchy-Wilshire plant matrix here, and we have the linearized CR3BP plant matrix here, which is applied by, if we take these equations and we linearize them relative to a libration point, say like the L2 point, for example, we end up with something that looks like this. And you can see they're pretty similar. We have 1, 1, and then 2, 2, and so it's the mean motion in this case is non-dimensionalized. So otherwise it would be much more similar. And can anybody guess why this is the case, that they look so similar? Or think, yes, Anna.
Well, I mean, wild guess, but maybe because in the relative motion, it's all with respect to your chief, and then here we're also kind of like with respect to this rotating frame, kind of like as the chief. Yeah,
so that's a good step in the right direction. Yeah, you're on the right track there. So the chief in the relative motion, we're talking about three bodies in both cases, right? When we talk about relative motion in the two-body problem, we're talking about the Earth, a chief, and a deputy. And in the absolute three-body problem here, we're talking about the Earth, the Moon, and a spacecraft, right? And if you take the mass of that second object, so the Moon, and you drive it towards a limit of 0, then you yield the same exact thing as the two-body relative motion. And this is actually why the Hill-Cauchy-Wilshire equations are called the Hill-Cauchy-Wilshire equations, because in 1878, George Hill published his researches in lunar theory, which described the relative orbital motion between the Moon and the Earth, and he came up with similar equations of motion. And then more than 80 years later, in 1960, Cauchy and Wilshire published their paper on the equations of motion for a satellite, a formation of satellites in Earth orbit that built on the same principles that Hill started with. So it's really all the same, started from the same fundamental system of three bodies, but then it added, you restrict the mass of one particle, and then you restrict the mass of the other particle, and you end up at the two-body relative motion. Yeah.
I didn't want to mention this. I wanted to mention something regarding the nonlinear equations.
Oh, okay.
Go
Yes.
one step back.
This one?
Yeah, here. Do you recognize the structure of those equations? How are they called in for the relative motion? You have time derivatives. These are not normalized.
Yeah, this is time derivative.
Time derivative.
Yeah, not with respect
If
to.
you use derivative with respect to anomaly, do you recognize them? So the Chandra-Hamilton equation. Same structure.
Yeah, that's true as well. Yeah, if you were to parameterize it with respect to the.
Different definition of the potential.
Yes. Yeah, so with respect to is represented as a W. Yeah. So yeah, think. Okay, so we've established that parallel, and now some more diving into what orbits and motion forms in the absolute CR3BP. These are some of those halo orbits that I mentioned before, and you see it's very different from Keplerian motion. They're forming kind of in between the libration point and the moon, and they're forming in families, not with a focus centered at either the libration point or the moon, and not in a standard ellipse in their kind of warping as they move in and out of the plane. So that makes it hard as well. And here's another family of Lyapunov orbits that are two-dimensional. But you see again, like kind of irregular motion, hard to parameterize both dynamically and geometrically. And here's something I just want to introduce quickly that we won't. That'll become more relevant later. It's the concept of invariant manifolds, and it's just really tied to the concept of the CR3P monodromy matrix and eigenspace. So every halo in Lyapunov orbit has a set of stable and unstable manifolds that correspond to their stable and unstable eigenvector that is that can be found from taking the eigenvalues of the monodromy matrix, which I'll define. So basically, if you integrate numerically the CR3P nonlinear equations of motion over a whole period, and you find the state transition matrix at the end of that period, that's known as the monodromy matrix. You take the eigenvalues of that and the eigenvectors associated with them, and you go down the stable one, then you end up on the stable manifold that propagates back towards that manifold will propagate and end up land you back onto the original periodic orbit that you started on. If you get onto the unstable manifold, that'll spiral away from that periodic orbit. Yes.
Sorry, what's a Lyapunov orbit?
Oh, sorry, that was this one, the two-dimensional one. Yeah, there's many other more families than we have time to discuss today. Butterfly orbits, vertical orbits. There's so many different types of interesting periodic orbits that can be found in CR3BP space. But just keep the concept of stability and eigenvalues and eigenvectors in the back of your head as we proceed through the rest of this lecture. So let's get back to our motivation. We want to explore the cislunar space. We know this new cislunar ecosystem and economy is coming, and distributed space systems are going to be necessary to accomplish the goals in that new space. A relative motion in the two-body problem is parameterized in many different ways. There's different solutions such as Hill-Colosi-Wilshire, Yamanaka-Ankerson, and Willis-Level-D'Amico, and other solutions that have been found in the LVLH and RTN, those local frames. And there's been different formulations of relative orbital elements found as well. And relative orbital elements, as you've learned in the last couple lectures, offer several key advantages, both in characterizing the motion geometrically, giving a better interpretation, having state parameters that vary more slowly, and the ability to control the spacecraft better in set conditions like passive safety through like EI vector separation, for example. Our relative motion in the three-body problem occurs differently. In the two-body problem, you have each spacecraft is on a periodic Keplerian orbit around the Earth, and you're taking kind of the difference in position or phase space between those to come up with your relative orbital elements. But in the three-body problem, you can have your chief spacecraft on a halo orbit, a periodic or absolute orbit, but your deputy spacecraft will be on a quasi-periodic orbit that forms about that periodic motion. And so for the deputy spacecraft, there's not really, it has no defined, the Keplerian orbital elements aren't valid anyway, but even if they were, like there is no defined like 7 major axis or things like that for the deputy spacecraft. And we can see it traces out through that quasi-periodic motion. It's making an orbit similar to the chief spacecraft, but not returning to the exact same point. There's an angular offset. And so over time, it'll trace out this torus structure. Torus, kind of like a donut or a bagel. It'll form this kind of mesh of quasi-periodic orbits. And so, just to drive home the point, it makes it harder to define the absolute orbital elements aren't defined in CR3BP space, such as eccentricity, semi-major axis, things like that. I mean, you can try to define them by using the moon as the central body, but you'll find they vary, they don't stay constant, they vary just as much as the position and velocity. And it's also difficult, again, because, as we mentioned before, the focus of the orbit is not the moon or the libration point.
I'd like to mention one point, that there is a regime where the perturbed two-body problem assumption holds. And that's for example, low lunar orbits.
Yes.
Or LFO, frozen orbits, for example. And then it's perfectly legitimate to use our two-body problem because the third body influence is negligible.
Yes, if you're very close, yes, that's true.
For example, for the Lane mission
Mm-hmm.
and other that are closer to the moon, it's just a two-body problem.
Mm-hmm. Yeah. Thanks. Yeah, that's a good point. There are some reasons where it does hold, but in general, if you're at a halo orbit a little further away, then the absolute orbital elements won't hold, and then when you try to form those quasi-periodic orbits, your deputy won't have any orbital elements of its own, so then you won't be able to formulate ROEs in the same way that you can in the two-body problem. But that's why we're here. How can we figure out a new dynamics models and what currently exists already to characterize this relative motion in the three-body problem? So here's one approach. This is a linearized model that starts by using a Taylor series expansion to linearize the absolute motion of the starting from the CR3BP nonlinear equations of motion, linearizes them about the libration point. I italicized that just because it's what you take you'll see it in the successive dynamics models where we take the linearization about becomes pretty key. And then so they linearized about the libration point, and then the state vector they used was the difference between the chief and the deputy in Cartesian space in that synodic rotating frame. And then what they found is the linear absolute motion and the linear relative motion plane matrices were identical. It was just a matter of changing the state vector because they were just subtracting the two identical equations of motion. And they were able to apply LQR control to that and use that linearized dynamics model. So there's one approach. Some other authors have dived more deeper into the quasi-periodic tori structure and focusing on making this torus map, like how do we map from the normal Cartesian dynamic space to torus space, to this torus parameterized. It's a two torus because it can be parameterized by two angles, theta 1 and theta 2. The revolution around the central body and the rotation where it is relative to the ring of the ring of the torus. And so they took several authors have taken this approach of taking multiple approaches. First, you could just define the quasi-period orbits themselves by taking a perturbation from the original absolute orbit and simulating those quasi-periodic orbits and finding that QPO family. And then you could also try to look deeper at the relative motion, the difference between those or spacecraft on a quasi-periodic tori, and take the difference between torus phase angles. You have here this delta theta as your state vector. So they're relying pretty much entirely on just these torus angles to maintain the separation or control the separation in the way that they want for their formation. Then we see another approach called modal constants or fundamental solution constants, which is basically just decomposing the spacecraft relative motion as a sum of the individual modes associated with each part of with each eigenvalue. So this is why I said that monodromy matrix that we mentioned earlier will come back in handy. So when we look at the eigenvalues that result from this CR3P, they could either be the zero eigenvalue, which is just the trivial mode associated that it's already on when it's on the periodic absolute orbit. They could be a pair of complex eigenvalues that correspond to a center or oscillatory node. There could be a real positive eigenvalue, which is an unstable mode associated with that those invariant manifolds, the unstable invariant manifold. Or there could be a real negative eigenvalue, which is a stable mode, drives the motion towards the periodic orbit, and that would be corresponding to your stable manifold. So these different modes, so there's always a space. This is a six-dimensional system, so it would always have six eigenvalues. But sometimes there's they come in different pairs than the others, sometimes depending on the stability of the orbit. So sometimes you could have two pairs of complex eigenvalues, sometimes you could have one pair of complex eigenvalues, a real positive, a real negative, and the pair of Zeek eigenvalues. But the point is that through this approach, they were able to decompose the satellite motion into each mode and then control those modes individually. They're turning them off or just, using those as integration constants, basically. So now we're going to look at CR3P relative dynamics in the local frame. So up till now, most of the systems we've been looking at have been formulated in still using that synodic rotating frame. But if we, while we're in our synodic frame, we look at the, we can define a chief-centered, moon-anchored local frame, either an LVLH frame or or any other type of local frame. For example, you could have a frame definition where, like the NTW or TNW frame, where the velocity vector is one of your unit vectors on the axes. But since you're familiar with the RTN or LVLH frame from the previous lectures, we'll introduce it this way. And note that the angular velocity vectors and the position vectors, it's all relative to this, to the periodic halo orbit that the spacecraft is on, which means the velocity vector is also that we use when we do r cross velocity to define the angular momentum vector. That's all with respect to the moon synodic frame. So just to be clear there, because sometimes if we define this in the inertial frame, it may look like a different frame. And so if we go into this local frame, and where we have a chief and one or more deputy spacecraft, and we do the linearizations with respect to that chief spacecraft position, that allows us to have probably the best system of equations of relative motion we can get in the CR3BP. So we're going to start off with the state vector of our deputy, which is just this row here, the relative distance in the local frame with respect to the chief. And then we're able to derive a set of linearized equations of motion in state space form, which I've expanded out here, which you can see some familiar terms just related to the gravitational forces exerted on the spacecraft from the moon and from the Earth. The major difference, or not difference, but the major step that's been taken here is that the linearization is being done with respect to the chief spacecraft position. So that's why in these terms here, it's R, which R is the chief spacecraft relative to the moon. It's R plus the vector from the Earth's position to the moon, and R relative to the moon here, not R plus rho. So we've taken that rho term out and linearized using a Taylor series expansion, and linearized with respect to just the chief's position only. Taking it out is a simplification. That's why we have this expansion here, partial derivative terms. But the key step here, the key takeaway here is that we're able to isolate the state vector, the rho and rho dot, in a way that allows us to represent it in a linearized state space form. Yeah. And here we have, so those tori that we talked about before, and we saw kind of the picture in the synodic frame, we can actually visualize them in the local frame as well, now that we have this definition of the dynamics. And so these videos, which Yuji beautifully put together, we can see how formation of spacecraft, a swarm of spacecraft at different initial starting points evolve over time, over an orbit, in different local frames. So you can see they're making quasi-periodic motion. They don't return to exactly the same point, and they're fluctuating around, but they are maintaining separation relative to the origin, relative to the chief.
Is there a condition similar to the energy matching condition here? Using
Like commensurability, like?
Yeah, using the Jacobi constant.
Like to accomplish which purpose?
Periodicity.
Yeah. Well, they would all have the same Jacobi constant as an energy as the absolute chief orbit. So, yeah, so it's tricky to say that because I think they would all be energy matched already. Yeah. Yeah, and one more takeaway here is that the large oscillations, those are occurring at perilune. And perilune, you've dealt a lot with periapsis, perigee in the Earth case. Perilune, when the spacecraft is closest to the moon, say at, go back. The top of the perilune there, that's when it's just like in Earth orbit, that's when it's moving the fastest, and that's when the dynamics are evolving more rapidly, and therefore the linearizations are more prone to error and breaking. And just so that leads to the oscillations we see here, and just the dynamics are evolving, and also it makes the system harder to control at those regions as well. Emily?
Apologies if I missed this earlier. What is the TNW frame?
Yeah, so I didn't really define that. I only defined it very briefly, but since I was focusing more on the LVLH frame, but basically it's similar. It's another version of a local frame, and it has the one unit vector pointed in the velocity direction of the spacecraft, as opposed to the position direction, and then another unit vector also pointed in the angular momentum direction, and then the right-handed triad is completed with some inverses like negatives, I think, thrown in just like there is in the RTN and LVLH frame. But Vallado defines it as the NTW frame, if that's a reference that anybody wants to look up later.
I've seen it on Schaub,
Okay.
the model track, when we introduced that frame in the two-body problem.
Okay. Yeah, the TNW frame offers some advantages. For example, the large oscillatory motion is more limited to the velocity direction. So it's helpful with characterizing uncertainties and visualizations. So now we're going to take a deep dive into one dynamics model called local toroidal coordinates. And we'll start by comparing it to relative orbital elements theory. Again, bringing back to our monitoring matrix and our eigenvalues. So in the restricted two-body problem, all 6 of the eigenvalues of the monitoring matrix are equal to 1. So this is a central mode. That's how we get periodic motion in the restricted two-body problem for relative motion. In this circular restricted three-body problem, we have at least 2 complex eigenvalues that have a norm of 1, but still they're complex, so this is an oscillatory mode. So, and that's how we get the quasi-periodic motion. And so we can see in the restricted two-body problem, we have an osculating relative ellipse where the relative orbital elements can define the size and shape of that ellipse. But we know that also that unless there's perturbations involved, ROEs are generally time invariant, which is how we are able to get periodic motion in ROE space and in two-body motion, problem motion space. Now let's look at kind of not exactly the same thing, but kind of a parallel, the osculating invariant circle in the CR3BP, which is parameterized by the eigenvector of the oscillatory mode of the the chief spacecraft's orbit. So here, this eigenvector is time varying, so it keeps moving and tracing out this. This circle keeps changing as the eigenvector evolves, and the eigenvector keeps redefining the shape of the invariant circle. But the key thing here is that we can use that oscillatory eigenvector to parameterize our spacecraft motion. So we define the system. Well, we didn't. So this work was first defined by Elliott at student at UC Boulder. So local toroidal coordinates, as they're known, basically maps the motion along the with respect to the oscillatory eigenvector. So we have the imaginary part of the eigenvector here, the real part of the eigenvector here, and then the right-handed triad is complete. That's our local toroidal coordinate frame. And then we can define either a set of polar local toroidal coordinates based on the angular separation between them, or non-singular local toroidal coordinates, which are just with respect to the vector bases. And we can set a condition for quasi-periodicity, which basically sets a lot of the coordinates and their derivatives to 0, basically saying that the spacecraft has to stay, the deputy spacecraft would have to stay on this invariant circle on the oscillatory eigenvector to be considered in experiencing quasi-periodic motion. And the key thing here, why would we want to define such a condition? As we saw from these images and animations, when we have this bounded quasi-periodic motion, then we're able to set passive safety conditions and enforce them, because we know that the deputy will not collide with the chief and will maintain whatever safe separation distance we define it to, even though it will oscillate around. And so here's an example of a reconfiguration using leveraging local toroidal coordinates that Yuji and I worked on, where it's we set up a non-convex problem with keep-out zones around the chief spacecraft, and then the key objective here is to reconfigure from one quasi-periodic orbit or torus to another at a smaller magnitude. And so this image doesn't really tell you much except that the transfer was successful. But the key thing here is when you look at it in local toroidal coordinates, we have the invariant circle of the smaller torus and the invariant circle of the initial starting larger torus. And we see that if we apply these other methods in blue that don't leverage local toroidal coordinates, the spacecraft does not stay within the invariant circle. And this could leads to a loss of quasi-periodicity and loss of passive safety. However, if we see the magenta trajectory here in local toroidal coordinates using the non-singular local toroidal coordinates, at every step along this trajectory, passive safety is enforced. It's always on a quasi-periodic orbit, a quasi-periodic torus, until it reaches its final terminal condition. And so this is a pretty effective and practical way to set a safety condition by leveraging the properties of local toroidal coordinates. So that's the majority of what I wanted to cover. Just to wrap up with some key takeaways from what we've learned here today. From the start, we established that CR3BP and two-body problem motion, both absolute case and relative case, are very different. And we've looked at the quasi-periodic and torus structures that can form in the CR3BP, and how that relative motion, that influences the relative motion. And then we looked at several different dynamics models that have been employed to characterize and control CR3BP relative motion and the different linearizations and approaches that each author took. And we focused deeper in on local toroidal coordinates, which is an area that we've been working on more and more, and how that can serve as a substitute for ROEs, at least in some ways, to set these safety conditions and enforce that bounded periodic motion. And I want to be clear about what we're doing there. If we go back to, sorry, it's a little out of order, but if we go back to this modal constant approach here, this is the local toroidal coordinates is basically a subset of that. It's ignoring the positive and negative eigenvalues and saying that, you know, we don't want to drift or either way. We just want to stay on that center oscillatory mode, and so we're only going to focus on that part of the eigenvalues and enforce that condition. And to wrap up with some extensions for where this relative dynamics and three-body problem could go in the future. Remember, the title of this lecture is Relative Dynamics in the Three-Body Problem, not just the CR3BP, because the key thing here is we want to be able to achieve the mission goal of operating distributed space systems in cislunar orbit or any other three-body system safely, effectively, and efficiently. And the CR3BP alone, it's a great starting point, but it's not the only way to characterize the motion, nor the best way in a lot of cases, because of the circular assumption. Because the Earth and the Moon don't move in a circular orbit, there's actually an eccentricity of about 0.05, which doesn't make a big difference in your modeling at the start, but if it's an actual mission, that would make a huge difference. So that's why models in the elliptic restricted three-body problem, which does take that eccentricity into account, although then the model becomes more complicated, that's a next stage to progress some of this work on relative motion and relative dynamics models, as well as the bicircular restricted four-body problem, which takes the sun's motion, motion and gravitational force into account. That's very effective if you're dealing with, for example, a heliocentric disposal trajectory, where you have an orbit, a spacecraft in orbit around the moon, and you want to dispose of it at the end of its lifetime and send it into a heliocentric transfer. You would take into consideration you need to take into consideration both the Earth, Moon, and Sun. And of course, at the very top of the list, we have high fidelity ephemeris modeling, where you're really using like the actual positions of the Sun, Earth, Moon, whichever, and all the other perturbations like oblateness and solar radiation pressure that are necessary to really get the most high fidelity modeling possible that you would need for a real mission. So the point is that research into relative dynamics, not just research, but work and actual implementation on relative dynamics in the three-body problem doesn't stop just with the circular restricted three-body problem. There's a lot more steps to go, and that's what we're continuing to work on. So that concludes the lecture, and I'll take any questions now. Yes, Professor.
What if some of the students, would like to implement these models as part of their project, or so? Do you have any guidelines, suggestions, tips on things that could be hard, easy, where they could get stuck? Because the models can get quickly quite complicated, and then when we talk about depending on orbits, interesting everybody problem, you have to find those orbits.
Yes.
So it's not that immediate as in the two-body problem. So any wise suggestions or warnings that you would like to share?
Yeah, like I can talk about at least what when I took this class, and my class partner was Jared Blanchard, who also worked on the restricted three-body problem for his research. So we did a project together on three-body dynamics set in around Enceladus, the moon, and we took the quasi-periodic approach, kind of that second one. I mentioned based on the work of Olakara, to kind of find those, first find the absolute orbit and then the quasi-periodic orbits that come off of those, and then try different control techniques. And I think there were parts of the course, though, where we did simplify it down to a two-body model just to make it, just so we got the most out of the course in terms of learning about relative orbital elements, because there aren't really those kinds of parameterizations that you can use easily for the three-body problem, right? Unless somebody wanted to try implementing local toroidal coordinates, I guess. So, so I would say to, you'd have to just think outside of the box, I think, a bit more, because the dynamics are so nonlinear, and maybe implement different control strategies than the ones that are taught in class for the two-body problem. But I would also say that, there's a wealth of literature out there now on the quasi-periodic tori and those things, especially from Shear's lab in UC Boulder, and Anshu.
So when you mentioned the passively safe orbits, is that passively safe for a satellite in the three-body problem? And if so, is there also a situation where you have two satellites formation flying and they are not drifting with respect to each other, if they're both in a passively safe orbit?
Two satellites, like two deputies, you mean? Like,
yeah, or I guess if there's the chief and the deputy, and they're both in a passively safe orbit, is that a situation where the deputy is not drifting away from the chief, or would there be drift?
Well, no, because remember, we're in this approach, we're turning that drift node off and just focusing on the oscillatory, the quasi-periodic node. Does that make sense?
Okay.
So the spacecraft, it won't just form a nice ellipse or circle, but it will remain bounded within this torus.
Okay. So this frame is in like the chief's alveoli. Okay.
Yes, this is in the chief's alveoli, and the chief is right there.
Understood. Sorry, I misunderstood. Okay. Yeah.
No, good question, Tycho.
I'm curious, do you know if Apollo back in the 60s, because I'm assuming they didn't have all this fancy stuff, they could just assume that it's the two-body problem because they were so close to the moon, like specifically when the lander was meeting up with the orbiter?
Yeah, so that's a good question, and that goes back to, I think, some of the things Professor D'Amico talked about, where there are situations where you can assume two-body motion where you are that close. And that's another thing for the projects, too, if students wanted to pick a closer orbit, where you can make those assumptions without having to deal too much with the 3BP. But, for the Apollo missions, they would have to do, I believe, like kind of patch the trajectory a bit. So, like, when they were transferring to the moon, of course, then they would have to take both into account, right, the Earth and the moon's gravity, to accomplish that transfer. And then, and then once they're like right about to land, they would have to then it would be more just the moon's dynamics, and as well as like other things like the moon obliqueness and J2, et cetera, perturbations that play more of a factor there. But does that answer your question?
Yeah. I was just wondering, like.
But the Higgs equations were developed for that purpose.
Right.
Gemini and then Apollo for rendezvous and lunar orbit rendezvous.
Right, and they're
which are close enough to the moon where the other effects are negligible. But for the absolute trajectories, Walter is saying you need to take that into account for the transfer. Yeah. Consider that we are now, I mentioned the Starlink mission in class, the Swarm 4 management NASA. And we are discussing with NASA about the successor of the Starlink mission around the moon. And the NASA team is looking only at orbits that are two-body prone. It's much simpler.
Right.
Gateway, which is planned instead on an RHO, which is an halo orbit, that would be a different regime. But it's farther away from the moon. So it depends on the application you have.
So around this slide, and I think a few prior, you talked about the decomposition into the different modes. Could you share a bit more about what you mean by sort of removing some of those modes, like the drift mode that you just spoke about? Is that a matter of selecting a particular orbit that doesn't exhibit that mode, or is it a matter of sort of neglecting it from the modeling to show what the behavior of the other modes is?
No, it's a matter of like, yeah, so you do start with all the modes, and then, but these yield basically, they call it the modal constants approach, but it's basically integration constants. So if we have, so based on your initial conditions, and if you map those to integration constants, then you could set the integration constant, you have 6 constants, you could set the one that corresponds to the drift node, you could set that to 0.
It's like a design problem.
It's a design, yeah, it's a mission design. So you turn that node off, and then you turn the other ones on when you want to. This approach, so the local toroidal coordinates and the quasi-periodic approach we were talking about, that sets, just assumes that all those eigenvectors are associated with the unstable modes, and other modes are set to 0, and we're only focused on staying on the oscillatory eigenvector. But there's some flexibility with this approach, because maybe during a reconfiguration or transfer, you would want to turn the drift mode on, right? So to enable you to maneuver in a certain direction or away from the chief spacecraft. So sometimes having it set to 0 is not necessarily a bad idea.
I'd like to make a comment which is a little bit counterintuitive. When you do the comparison or analogy between the two-body problem, the ROEs, and the restricted three-body problem, if you go back to that slide. Now, it turns out that the condition of passive safety, and when we speak about passive safety, it means that if you interrupt control at any point in time, the natural motion of the satellite will be such that there is a misdistance between them. And it turns out that the condition of passive safety in halo orbits is much stronger than the condition of passive safety in the two-body problem, especially if you are close to the Earth. As we will see in the next lecture, Earth obliqueness causes a rotation of the relative eccentricity vector. And so that nice, beautiful ellipse in the plane perpendicular to the flight direction that we obtain by setting up parallel relative eccentricity inclination vector is broken because the relative eccentricity vector rotates, and so the angle between the two increases, all the way then to become 90 degrees perpendicular, where it becomes a degenerate line. If you exploit nonlinearities, you can get to conditions that ensure some passive safety also beyond that, but they are not so practical from an application standpoint. And so the analogy would be even interesting to see if you include F obliqueness effects in this state transition matrix, which provides a rotating eigenvector. But to me, from what I see, it looks like that leveraging the torus for passive safety is is a stronger condition than what you can obtain around an oblate planet due to perturbations.
Sure. Yeah, if you were to then add like lunar oblateness, of course, then maybe it would be different. But yeah, but that's another step forward.
When we are closer to the moon.
Yeah.
Very interesting. Is anybody looking at moon's orbits or restricted three-body problem for their projects here?
We're doing Grail.
Agree.
We're taking it easy.
Not very.
Yeah. I think mine and Jared's project is shared with on Canvas. If anybody wants.
We should have not shared it, not to scare. There are other questions?
How do perturbations such as solar radiation pressure affect this kind of approach to modeling the relative orbits?
That's a good question. Yeah, and that's something we're trying to incorporate into work in progress is modeling that solar radiation pressure. I think the modeling so far. Where's a good slide? Yeah, I think the modeling. It is definitely a significant perturbation. I think, though, that in our high fidelity modeling so far, the eccentricity of the lunar orbit has more of an effect, causes more error than the solar radiation pressure. Because that eccentricity of 0.05 and the moon have actually the moon and Earth varying in their distance, and so therefore varying in how much gravitational force they exert on the spacecraft. That makes the most difference. And then you'd add SRP on top of that would be the next biggest step. Yeah. So. Yeah. Does that answer?
Yeah, it's not the top priority in terms of modeling.
Yeah, it's still a priority. Like we're still we want to. Yeah, if we could come up with like a state transition matrix study.
Information flying between solar states.
Yeah.
Cool.
Yeah. Solar. Yeah.
Thanks.
Yeah.
Thank you very much.